Hey everybody, and welcome back to another lecture video. This time we're doing chapter 10, and chapter 10 is all about chemical bonding. In 1989, researchers discovered the structure of HIV protease. All right, for you, HIV protease. This is a protein that's synthesized by the human immunodeficiency virus, HIV, which causes AIDS. So this is a protein that the virus makes. Now, researchers used bonding theories and models that predict how atoms bond together to form molecules to simulate how potential drug molecules would interact with the HIV protease molecule. And so we're going to go over those bonding theories and models that the researchers ultimately relied upon. Now, in this image that I'm showing you, the gold-colored structure on the computer screen is a representation of the HIV protease. The molecule shown in the center, this guy, is indinavir. You can see the name written there. Indinavir, it's a protease inhibitor. So it actually goes and it inhibits the function of that enzyme. Now, without HIV protease, HIV could not spread through the human body because the virus could not copy itself, and AIDS would not develop. AIDS is the disease that arises from you being infected by this virus. So with knowledge of the HIV protease structure, drug companies designed a molecule that would basically disable the protease by sticking to the working part of the molecule. We call that the active site. If you ever take Chem 21, which I teach in the spring, we go over enzymes and enzyme activity, and we talk about active sites and inhibitors and that kind of stuff. So by the early 90s, these companies had developed several drugs actually that would inhibit the HIV protease, and they called these protease inhibitors. In human trials, protease inhibitors in combination with other drugs have actually decreased the viral count in HIV-infected individuals to undetectable levels. So although these drugs don't cure AIDS, the HIV-infected individuals who regularly take the medication can expect nearly normal lifespans. So that's the benefit. Now, bonding theories predict how atoms come together to form compounds, and they predict what combinations of atoms form compounds and what combinations do not. Now, bonding theories predict why NaCl and not NaCl2, why NaCl forms and why NaCl2 does not form, and why water is H2O and not H3O. And there is an H3O, and actually this was a bad example because H3O is what? Now, H3O doesn't exist. Let me back up. H3O doesn't exist. What does exist is the polyatomic ion H3O+, and that is called hydronium. And of course, this makes a difference. H3O and H3O+ are not the same structures. H3O has all of its electrons. H3O+ is missing an electron, and that's what makes this one possible and this one not possible. But again, that's what we're going to be talking about. Now, the bonding theories explain the shapes of the molecules, which in turn determine many of their physical and chemical properties. Now, the bonding theory that we're going to go over is called the Lewis theory, and it's named after G.N. Lewis, who was an American chemist. He died in 1946. We represent electrons as dots, okay? And we draw what are called dot structures or Lewis structures to represent the molecules. And these structures have tremendous predictive power. The Lewis theory can determine whether a particular set of atoms, like I said earlier, will form a stable molecule and what that molecule might look like. And although modern chemists also use more advanced bonding theories to predict molecular properties, Lewis theory remains the simplest method for making quick, everyday predictions about molecules. So in the Lewis theory, the valence electrons of the main group elements, right, are represented as dots surrounding the element or the symbol of that element. So the result is called the Lewis structure or the dot structure. And remember, the number of valence electrons for any main group element, except for helium, which only has 2, but is in group 8, is essentially equal to the group number that they're in. So oxygen is in group 6, 6A or 16A. Sometimes you see it written as, or 16 because they count the transition columns in the middle. There's 10 of those. Anyways, 6 electrons in the valence shell, which in the last chapter we saw meant, and they are in the outermost orbitals, highest principal quantum number. And then we see that on the right hand side, the symbol O gets these 6 dots around it. Now we don't spread them out like this. We're going to say electrons pair up, okay? And we're also going to say that they want to have 8 on the outside. So at the end of the day, if you had a dot structure that was totally filled up with electrons, you would have 8 around them, and they would be in groups of 2, so there would be 4 groups. Okay. Now this isn't the maximum number that any atom can have. It just so happens that if you are part of the first 2 rows on the periodic table, maybe this was a poor drawing. There we go. If you are one of these guys, and I know there's a 3rd row in there. Anyways, if you're one of the first 2 rows of the periodic table, you can have a max of 8 electrons. And we call this the octet rule. We're going to see that if you're in the 3rd row, which contains a D shell as part of it, you can actually have more than that. But for now, we're going to say most atoms are going to be stable when in their outermost shells they have 8. And this is, for the most part, true. So that's the dot structure for oxygen. Now I'm going to show you a few others. Now each dot represents a valence electron. And the dots are placed around, like I said, with a maximum of 2 dots per side. So it's important to follow this convention when you're doing the homework. We fill the dots in singly first, and then we pair them. So if you look down here from 1 all the way up to 8, you see that they go in by themselves. So these 2 are in their own little orbits. These 3 are in their own orbits. These 4 are all spread out. Remember, they're electrons with negative charges. They don't want to be near each other. And then with nitrogen, we have the first electron that has to pair up. Now, it doesn't matter where you put it. You could put it up here, you could put it here, you can put it here. What matters is that you have the right number. So yeah, don't worry so much about which side gets it first. It really doesn't matter. Sometimes people write beryllium like this. Hey, it doesn't matter. It depends on what you're doing. If your ultimate task is to show the dot structure for beryllium, like literally if I said show me the dot structure for beryllium, and you needed to write this would be the best representation because it shows the electrons spaced out. But if we are going to show how beryllium forms a compound with oxygen, then we do not need to be in this form. You could put your electrons on the same side. It doesn't matter as long as they're there. And you'll see, we'll do some examples. So Lewis structures allow us to easily see the number of valence electrons in an atom. That's the benefit. And atoms with 8 electrons, as I said before, are particularly stable and then can be easily identified because they have an octet. So we can try, let's see, what do I have? Okay, so let's try writing just a couple out here. So let's write the Lewis structure for phosphorus. Now, you need to know where that is on the periodic table. So phosphorus, you can see, is in group 5A. I don't have the ability to draw. Oh, I do. Can I erase? All right. Okay, yeah, so phosphorus right here, 5A. So we would jump back in here and we would say, okay, 1, 2, 3, 4, 5. Doesn't matter where you put them, I just happen to copy that one. Let's do another one. Let's do, how about bromine? So we go bromine. Bromine is going to be right here, right? We don't need, we can do a refresher on the electron configurations as well. It's got 35 electrons, but we see that it's in group 7. So I think that 2 and 2 and 6 is 10, 2 and 2 and 6 is 10, that's 20, 10 is 30, 35 electrons. We would look at the 4s and the 4p, 2 and 5 is 7. Of course, we already said it was in group 7. 1, 2, 3, 4, 5, 6, 7. So that's easy. You should have no problem drawing Lewis structures for elements. Now the next thing that you would do, let me see here. The next slide doesn't have, we're not there yet. We're not drawing ionic compounds. We'll be there in a second, but I wanted to just talk about the exceptions. Helium's an exception. When you draw helium's electron configuration, 1s2, we see that it has a full s shell. And that's stable. It's a noble gas. It's stable. So what we would do with helium is we would actually show it paired up. That one we would show paired up because these two electrons are a duet, and a duet is a stable electron configuration. Okay, so now that I've given you the one exception, let's go to chemical bonds. So in Lewis theory, chemical bonds involve sharing or transfer of electrons. And they involve, as I said, sharing or transfer. Sharing, we're going to call a covalent bond. Transfer, we're going to call an ionic bond. And in either case, the bonding atoms attain stable electron configurations. A stable electron configuration, again, it consists of 8 electrons in the outermost valence shell. And this observation leads to what we call the octet rule, that in chemical bonding, atoms will transfer or share electrons to obtain outer shells with 8 electrons. The octet rule generally applies to main group elements, with the exception of hydrogen, lithium, and beryllium. Each of these elements achieves stability when it gets a duet because it's so small, and it only needs, a few electrons to have a duet in its 1s or its 2s shells, the two lowest shells that it has. When we're talking about ionic compounds and we're talking about transfer of electrons, we know that when metals bond with nonmetals, electrons are transferred from the metal to the nonmetal. In the case of potassium, that's the metal, and chlorine is the nonmetal. We see that that's true, and we can visualize that with a diagram, a dot diagram that shows the dot structures of the elements reacting together. So the metal becomes a cation, the nonmetal becomes an anion, and the attraction between that cation and anion is what results in an ionic compound. And so in Lewis theory, we represent this by moving the electron dots from the metal to the nonmetal. So the potassium dot is on potassium. It would then move to the chlorine, and we see that it has moved to the chlorine. Now, what's the effects of losing an electron for potassium? Well, that gives you a positive charge. Now you have more protons than electrons because you were balanced and now you lost an electron. For chlorine, you've got an extra electron. And where you were balanced before, now you've got an extra one, you've got a negative charge. So you can see that this stabilizes everybody. Potassium, we know from the last chapter, now has a noble gas electron configuration. Its outsides look like the noble gas before it. And chlorine now looks like the noble gas that's right after it, because this was one away, this one was one away from looking like a noble gas on the outside, and potassium was one too many. All right. Now we usually show the structure, the Lewis structure of the anion written in brackets. So you can see that here. It's got brackets around it. Now that's just a convention, and the charge goes outside the brackets right up in the upper right-hand side. The charges are shown, but the brackets are not shown in the homework drawing program online, so just be aware of that. Now draw the Lewis structures of magnesium and oxygen. So you would get magnesium, you'd get oxygen. You'd want to know what where their columns are, right, in the periodic table. Magnesium is in column 2, so we could load him up. Oxygen's in column 6. Now I drew them like this so that I could draw my arrows really nicely. So what I'm going to do is I'm going to move an arrow to show that one of these electrons is going to make its way over to oxygen, and that the other is also going to make its way over to oxygen. Now that has the effect of putting charges on both of those, and then we could of course show them with the anion in brackets and the magnesium with its charge. Now we still show the dots. The dots are still shown. They're all over the oxygen. So we can do another one. This one had more charges than the sodium chloride did. We can do sodium and sulfur. It's a column 1, and sulfur is a column 6. Now, you can see that the sodium only has 1 electron to give, and yet sulfur needs 2. And so what will happen is, if you don't have enough electrons with one sodium, you got to bring in another sodium. And so now the sulfur is satisfied. Sulfur is going to get a 2 minus charge for gaining those 2 electrons. Now you can see shown here they don't have 2 sodiums. It's up to you to decide or to figure out that you need 2 sodiums. If we were to just transfer this one, this would be Na plus, and this right here would be sulfur minus, but it wouldn't be sulfur 2 minus because it doesn't have that remaining electron. Other atoms can come in here. A potassium can donate its electron, and we could end up with Na, K, it would be more metal first, so K, NaS. That's an ionic compound that's made up of 2 different cations and 1 anion. But this would be written as Na2S. And so before, when we were learning how to write the formulas for these compounds, these ionic compounds, we were actually doing it based on just memorizing their column and memorizing the charge that they form, and then doing a charge swap. Remember? 2 minus, 1 plus, and then we would bring the numbers, giving a 2 and a 1 down below. Now we actually see that there's a reason that they're forming those charges and why there needs to be 2 sodiums for every 1 sulfur. It has to do with the amount of electrons that they can give. Okay, so that's ionic compounds. Let's talk about covalent compounds. So again, covalent means sharing. When nonmetals bond with other nonmetals, the molecular compound results. Molecular compounds contain covalent bonds in which the electrons are shared between the atoms rather than transferred. And so in Lewis theory, we represent covalent bonding by allowing neighboring atoms to share some of their valence electrons in order to obtain octets, or duets in the case of hydrogen. So you can see here in this example, if we were going to let these nonmetals, which hydrogen counts as, share with each other. And actually, let's do a simpler one first. Let's do H and H. If we let two hydrogens react with each other, their two electron orbitals will come close and actually overlap with each other. Got a package. And they are able to form a molecule. And we always represent the overlapping of two electrons as a bar. So a bar in between these, this would be H2. If we look at the case for H and O, we see that hydrogen can definitely donate an electron to oxygen, but that's not going to be enough to satisfy this oxygen. The oxygen needs another hydrogen with another electron. And only then would we be able to form the molecule of water. Now you can see here, if we put the hydrogens on either side, it looks a little more symmetrical. And if we kind of visualize it this way, the orbitals of the hydrogen and the oxygen overlap. Now for hydrogen, it's happy to only have two electrons because it only has a 1s shell that it needs to fill, and this satisfies that. For the oxygen, this has the 2s, 2p, 6 shells that it's filling, and it's normally 2s, 2p4. So by gaining two extra hydrogens, or being allowed to share them with the hydrogens, it's able to attain the electron configuration that it wants. So this is part of the predictability of these models or these theories, is that we can see what atoms will connect with each other and which ones won't. Like we would see that Na and potassium, wouldn't connect with each other because neither of these wants an electron. So neither of them is going to be able to give an electron to each other. Okay, so the shared electrons count as part of the octets or the duets for both the atoms. So they don't just count for one atom or the other. Now electrons that are shared between two atoms are called bonding pair electrons. That would be those electrons, if you're looking at the other graph, or the other diagram. The electrons that are only on one atom are called lone pair electrons. And oxygen in water has two lone pairs. Now, bonding pair electrons are often represented by the dashes to emphasize that they are a chemical bond. So again, like that. Each dash represents a pair of electrons. So there would be two electrons there, two electrons there, two electrons there, and two electrons there. So Lewis theory does explain, does explain why the halogens form diatomic molecules. I showed you hydrogen already, how hydrogen forms. It's a diatomic molecule, but it's not a halogen. Again, it has one electron and it wants to share that one electron. Now for things like chlorine that have one electron away from being noble, or in other words, have 7 valence electrons, we can see that by allowing these guys to get close to each other, they are able to share that electron, or to share one set of their electrons. And so again, we would have these orbitals overlapping, and they would be chemically bonded in that sense, and we say Cl2. So you would still show them with all their electrons, but they would have 3 lone pairs apiece and a bonding pair. So hydrogen and all of the halogens will form compounds this way to form the diatomic molecules. We can see in the few other diatomic molecules, such as oxygen and nitrogen, how that works as well. So let's take a look at oxygen. Now with oxygen, we know from chapter 5 that it exists as a diatomic molecule. We know it's an O2. If we pair two oxygen atoms together and try to find a Lewis structure, we find that there's not enough oxygens, an oxygen atom. What am I trying to say? We find that there are not enough electrons to give each oxygen atom the octet. So there's a total of, 12 electrons in here total. You see that if we give one oxygen an octet, that only leaves 4 electrons to put around the other oxygen, or for that one to have on its own, which gives it only a total of 6 and not 8. We could try moving that lone pair over to the other oxygen, but that just flips the problem around, and now the other oxygen doesn't have enough either. So there is a solution to this. We can convert a lone pair into an additional bonding pair by moving it into the bonding region. And then this is just, of course, the model. This isn't what nature does. Nature has a much more complicated way of this double bond forming, and we don't go into it in Chem 20, but in Chem 1 you may go into it. Here we're just going to say the ability to form double bonds and triple bonds is possible. So by allowing these oxygens to share more than one set of electrons, we can even it out so that by sharing 4 and keeping 4 to themselves, they both still have 8. Let's look at nitrogen. Nitrogen is another molecule we know exists as a diatomic molecule, N2. We can see that nitrogen with its 5 valence electrons would have 10 total. If we spread those around, each nitrogen only gets 6, and so they're both short. If we try to put the other set on one of the nitrogens, then one of the nitrogens only has 4, so the problem gets even worse. The only way for this one to work is if they share not 1, but 2 sets of electrons. Even giving nitrogen a double bond, 2, 4, 6, 8, 10, doesn't change the problem for one of these nitrogens that only has 6 electrons. So they have to share an additional set. And by doing that, they are able to obtain electron configurations that are like the noble gases. So double bonds, triple bonds, single bonds, these are all possible. Now, when 2 electron pairs are shared between an atom, the resulting double bond is actually shorter and stronger than the single bond. So for example, the distance between an oxygen nuclei and an oxygen-oxygen double bond is about 121 picometers, and in a single bond, 148 picometers. So this double bond means that they are closer together. It also means it's harder to get them to break apart, and it goes into the energy. So it's a stronger bond, and it's also a shorter bond. Now, while Lewis theory does correctly predict that a double bond for oxygen, it is actually insufficient to explain the paramagnetic properties that we see in oxygen. And so what I'm saying is oxygen actually has a magnetic nature to it. Liquid oxygen we see reacts to magnets, but the Lewis structure gives us an idea of every electron being paired up, which is exactly what not being magnetic is all about. So this problem led to the development of other bonding theories. Now we're not going to go into too many of the other details of those bonding theories, but just be aware that there are, let's see, what are they? It's the theory of hybridization that does go on to explain a few more properties of oxygen, as well as a molecular orbital theory that we're not going to look at. That actually does explain and shows very precisely that oxygen does have magnetic properties. Let's talk about the triple bond real quick before we move on. The triple bond is even shorter and stronger than the double bond. So if we look at nitrogen, a nitrogen-nitrogen triple bond, this is about 110 picometers, and a nitrogen-nitrogen double bond is only 124 picometers. And of course, we can have nitrogen do this. It just needs to be bonded to something else as well. And if you see this molecule, everybody would have an octet, except hydrogen, which would have a duet. And so this is a case of nitrogen having a double bond only. Nitrogen, of course, can also have lots of single bonds, but this number would just get bigger. This bond is actually so small and so strong that nitrogen gas, N2, is basically relatively unreactive. And so often in the lab, when we are worried about the air causing side reactions in our experiments, mainly the oxygen, we flood the system with nitrogen because it's a safe gas to use. All right, when we are writing Lewis structures for covalent compounds, there's a couple of rules that you need to kind of follow. Now, we want to write the correct skeletal structure for the molecules. We want to actually you can read all of these rules on your own. We're just going to do some examples. You read the rules. I'm not going to read the rules to you. Let's draw some compounds. So let's do carbon dioxide first, and then we'll do polyatomic ions. So carbon dioxide. So now carbon dioxide, one of the rules says first follow a symmetry guideline. Try to spread everything out so it's even and symmetrical. So that means if there's two O's, we're not going to put an O in the middle. We're going to put carbon in the middle. We're going to put O's off to the sides symmetrically. Now we're going to calculate the total number of electrons, valence electrons. Carbon has 4. Each oxygen has 6. So 16 electrons. Next thing we're going to do, or the way that I would like you to do it, is to do your bonding electrons first. So stick in your bonding electrons. So we've used up 4 electrons. There's 12 left. Then you go and try to give one of your atoms an octet. In this case, we've given him an octet. So this removes 6 more electrons. We're down to 6 electrons. If we do that for the other oxygen, we've given both of our oxygens octets, but we're out of electrons, and we see that carbon only has 4 electrons. So that doesn't work. But we know that we can start putting in double bonds. So maybe this oxygen puts 2 of its electrons there. Maybe this oxygen puts 2 of its electrons there. We could have just had one oxygen do it. So let me show you what that looks like. Let's say that happened, that this oxygen actually donated both times. Everybody still has an octet here, but what we would find out in a later chemistry course is that this oxygen would have a positive charge on it, and this oxygen would have a negative charge on it. And while that may happen in nature sometimes and briefly, nature really doesn't like having separated charges. And you don't know how to tell that in this class, so you don't have to worry about it. This would still fit the octet rule. But the best structure here is going to be one where oxygen is double bonded to the carbons, and they both only have 2 bonds. In fact, let me give you a breakdown of the types of ways you're going to see these atoms. You are going to see oxygen with 3 lone pairs. It'll have a negative charge. You'll see oxygen with only 1 lone pair. It'll have a positive charge. But most likely you'll see it with 2 lone pairs, and it'll carry no charge. For nitrogen, sometimes it won't have any lone pairs on it. It'll carry a positive charge. Sometimes it'll have 1 lone pair on it, and it'll carry no charge. And in the event that those are really the only 2 ways you ever really see nitrogen. There are other ways, I suppose, but we're going to worry about it. This doesn't mean a triple bond. This just means 3 bonds to show you the difference. This is the exact same thing. This is an oxygen with 3 bonds and 1 lone pair. Okay. And carbon. We find it always with 4 bonds, never with any charges on it. All right, before we move on, let's do a couple more examples of some Lewis dot structures. Let's draw the dot structure for carbon monoxide, CO. So, atoms, valence electrons, bonding atoms first, 2, 4, 6, 8, 10. That's clearly going to leave somebody without enough electrons, so perhaps we need to bring in a triple bond. And this is actually how we see, excuse me, this is how we see carbon monoxide. And in this particular molecule, carbon has a positive charge. I lie, I'm sorry. Carbon has a negative charge. You wouldn't necessarily need to know that. Oxygen has a positive charge, so this is a neutral molecule, carbon monoxide, but you showing it just as like that would be just fine. Let's do nitrogen, dinitrogen monoxide, so N2O. Now in this case, I'll give you a hint. The oxygen is on the end. The oxygen is not in the middle. So you would go N, N, O. 5 and 5 is 10. Oxygen is 6. 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. Nitrogen in the middle doesn't have enough, but he's only short by a few. We might be able to do something like this. This would give us nitrogen, sorry, I put too many. 2, 4, 6, 8, 10, 12, 14, 16. So that would be a Lewis structure. Now, is this going to be the best Lewis structure? This gives a charge to nitrogen and a charge to nitrogen. So maybe not the best structure. We could probably try to find another structure, perhaps one that doesn't have quite so many triple bonds. Of course, there are things that we do in Chem 1 where we find the best structure that we're not going to worry about here. And I'm still in a Chem 1 mindset, so I apologize for that. This would be just fine. It satisfies the octet rule. Everybody has an octet. You would not need to show those charges. Okay, let's do some polyatomic ions. Let's do CO3 2-. Or we did we do cyanide? Let's do cyanide. So Cn- is cyanide. Carbon has 4, nitrogen 5. That's 9, plus there's another electron, so you want to count that additional electron. 10 electrons. 2, 4, 6, 8, 10. That's clearly not enough to give everybody an octet. So if we try this, then we do end up with everybody having 8. Now, I mentioned carbon doesn't normally want to have this type of form. What you would do is you just look at how many electrons carbon actually has that belong to carbon, and then you compare that to the number it wants to have. And carbon wants to have 4, right? We said that. Right now it has 5. That's an extra electron. So the carbon here would be the negative one. The nitrogen wants to have 5, and it does have 5. 1, 2, 3, 4, 5. And so the nitrogen's happy, just like that, with 3 bonds and 2 lone pair electrons. All right, let's do one more polyatomic ion, and then we will look at a different topic. I hesitate to do any polyatomic ion just because there are some that are the subject of the next topic, and I don't want to jump ahead. So let's do this one, NH4 plus, and we can even do OH minus. So NH4 plus, this has 5 for nitrogen. Each hydrogen has 1, so that would be 4. And this has a plus charge, meaning we're going to subtract 1. So this will give us 8 electrons. In the case of the hydroxide, 6 for oxygen, 1 for hydrogen, and then an additional 1 for the negative charge. So they both have 8 electrons. We'll put nitrogen, and then spread out the hydrogens around the nitrogen, and do our bonding ones first. 2, 4, 6, 8. That satisfies the octet. Now this is ammonium. We know this has a positive charge on it. The positive charge actually comes from this nitrogen. The nitrogen here only has 4 electrons, and it would normally want to have 5, and so it's missing 1 electron, and that's why it has the positive charge. All right, our Lewis structures for polyatomic ions we typically show in brackets. With the charge on the outside. Okay, for hydroxide, O, H, 2, 4, 6, 8. We know that when oxygen has 6 electrons, it's happy. Right now it has 6 just on its own, and then a 7th one, so it gets the minus charge. But we would show it like that. All right, polyatomic ions. Add the electron for the negatives, remove the electron for the positives. Now there are some exceptions to the octet rule. Let's talk about some of these exceptions. Now, Lewis theory is often correct in its predictions, but some exceptions exist, such as the molecule nitrogen monoxide. This one only has 11 electrons, and the Lewis structure is right, where nitrogen doesn't have an octet. Now it's impossible to write good Lewis structures for molecules with odd numbers of electrons, yet some of these molecules do exist. So we do the best we can. Another significant exception to the octet rule is boron. Boron tends to form compounds with only 6 electrons around them. So like boron trifluoride, or trihydrogen. And again, we find this in nature. Both of these exist in nature. Boron has no octet in both of these. So we know that there's some exceptions in that regard. Now, there's also exceptions with having more than 8. These were exceptions to having, or with having less than 8. And so compounds like SF6 and PCl5 exist, and I can show you sulfur. You don't even need to see me put all of the lone pairs on the fluorines to know that sulfur here has 6 bonds. 6 times 2 is 12. So sulfur here has 12 electrons in its shell. Chlorine here, phosphorus with 5 chlorines around it, each of those chlorines, of course, having all of their electrons. You can see phosphorus has 5 bonds, that's 2 electrons per bond, that's 10 electrons in its valence. What is this? Or in its, in its outer shell. You say 12? So these are what we call expanded octets. And the reason that these are octets, the reason these are allowed is because these elements that are in the third row, the third principal energy level, they have a D shell, a D subshell that they can stick electrons in, whereas the elements in the first 2 rows don't have those shells available to them. I mean, they do in an excited state, but not in a normal, we're going to find it everyday compound type state. But in spite of these exceptions, Lewis theory really does remain a powerful and simple way to understand chemical bonding. Now let's talk about some of the other neat things we see with Lewis structures. Now, with some Lewis structures, such as in sulfur dioxide, we can write more than one good Lewis structure. So if we take the 18 electrons that are found in the valence of sulfur and 2 oxygens, and we use them to put together a Lewis structure, we get something that can look like this. Now go ahead and count up the number of electrons. You'll see that there's 18. You see that everybody has an octet. But, so let me back up a second. If you did this step by step and you did bonding first and then, actually we should have done that together because this is a good example of, let me show you. So this is what happens when you fill up the octets on the outside first. We didn't do an example of that. So 2, 4, 6, 8, 10, 12, 14, 16. We've given octets to everyone on the outside, all the outside atoms, and we still have leftover electrons. So then we go to the inside atom, the one in the center, and put electrons on that one. So sulfur sometimes ends up with 12 valence electrons. You know, it would have 5 bonds and also a lone pair. But that's not going to happen with any of the molecules we look at. In Chem 20, in Chem 1 definitely you see those because you have to know the geometries of those. We won't have to worry about those, but it is possible. So that's what happens with the extra electrons. Now we notice that sulfur doesn't have an octet here, so oxygen has to donate. Now in this structure here, it looks like it was the oxygen on the left that actually donated into the double bond. And so what if it was the oxygen on the right? You might think, oh, that's the same. It's just the molecule turned around. Well, no, it's not really. It's not really. This is oxygen 1. This is oxygen 2. And if this oxygen 1 was an isotope of oxygen that was, let's say oxygen 16, and this one was oxygen 17, we would really know the difference that one of them was double bonded and the other one wasn't double bonded. So we would need to show all possible structures here. And the other possible structure is that the double bond is actually, double bond is actually to the other oxygen. And so these would be what we call resonance structures, equivalent structures that basically only differ in which electrons are being donated. So this structure here on the left would be existing like this, and then these 2 electrons would jump down and form a double bond. That would be too many for sulfur, so sulfur would then kick this back out. And that little rearrangement is what converts one form into the other. And now this form is more stable for a second, and then its electrons drop in, kicking these back out. And this would be happening in nature back and forth, back and forth, back and forth. The ability for these electrons to do this, to move back and forth between 2 atoms that'll accept them, these oxygens, that's what stabilizes this molecule. Molecules that can resonate or that can send their electrons around and back again are more stable than ones that can't do that, especially if they have electrons on atoms that don't really want to have electrons on them. And so the ability to resonate is a stabilizing feature. So this would be happening back and forth in nature, flip-flopping really, really fast. And there's no way to really, say that it's in one form or the other. In fact, we would really draw a hybrid structure and just show that both oxygens are bonded to the sulfur. And that there's a double bond character to both of the sides of the sulfur. Because really it would be like a half a double bond and a half a double bond on both sides. Okay, let's do another one. Let's do NO3 minus. So NO3, 5, 3 oxygens, 6 times 3 is 18, an additional electron, and we get 24 electrons. Nitrogen, oxygen, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we're out of electrons. Nitrogen doesn't have an octet. So one of these oxygens has to donate. That leads to us having a double bond here, or a double bond here, or we could get a double bond here, depending on which oxygen is actually donating. And really, we can think of it as every time there's a double bond in a position, one of these oxygens could just be sending their electrons in to make a double bond, therefore kicking that double bond back out again, or sending it to the other oxygen, kicking one of their electrons back out again. So this thing sort of runs around on the nitrogen. The electrons sort of just jump from O's to O's to O's, stabilizing the structure. So this would have 3 resonance structures because 3 oxygens have the ability to donate to complete the octet for nitrogen. Draw PO4 3 minus, and see how many resonance structures that one has. Okay. So now that we've looked at equivalent structures or resonance structures, let's talk about predicting shapes of molecules. So Lewis theory in combination with valence shell electron pair repulsion theory, or VSEPR, valence shell electron pair repulsion, is actually used to predict the shapes of molecules. So this VSEPR theory is based on the idea that electron groups, i.e. lone pairs, bonding pairs, like single pairs, I just call them single bonds, double bonds, triple bonds, that all of these repel each other. And this repulsion between the negative charges of the electron groups on the central atom will determine the geometry of the molecule. So for example, in carbon dioxide being the center, has 2 electron groups around it. It has 2 double bonds. Now these double bonds would be repelling each other since they are full of electrons, and so they would repel each other in this direction, they would repel each other in this direction, and they'd end up being as far away from each other as possible on complete opposite sides of each other, on opposite sides of the carbon. The bond between, or the angle between those bonds is 180 degrees, and you can see that here. Again, and this makes sense. This is the farthest away that these 2 groups can get from each other when they're both attached to the same sphere, or the same carbon, the same ball. So we call this linear geometry. And linear geometry is whenever you have 2 electron groups. So this is the case for carbon dioxide. This is the case for selenium dioxide, or selenium disulfide. Selenium disulfide for the cyanide ion. In this case, there's no center atom, but no matter which atom you look at, they have 2 electron groups, a lone pair and a triple bond. Triple bond counts as 1 electron group just like a single bond would count. Let's see, is there any other linear molecules that I can think of off the top of my head? There are linear molecules that don't necessarily only have 3 atoms in them, but we won't go into any of those in this class. So the next grouping is the 3 electron group, and we call that trigonal planar. Planar because they lay in a plane, similar to how, all the squares on a chessboard lay in a plane. They're all part of the same flat surface. A frisbee would be considered to be circular planar because it's circle shaped and it's flat and like a plane. Of course, it's not exactly flat. It's got some depth to it, or else you wouldn't be able to throw it or grab onto it. But that's what we call it, trigonal planar. Now, Typical example would be formaldehyde here, or any of those SO3s or NO3s that we looked at. We looked at NO3. I'll just draw one of the resonance structures. That's where all the charges are. This thing ends up being just -1 because some of those offsetting charges. But we see the nitrogen is surrounded by a double bond, a single bond, a single bond. It's the same thing here. Single bond, double bond. Those groups would spread out from each other. Now, the double bonds aren't exactly the same in terms of their repulsion power as the single bonds, and I'll tell you about that in a minute. But in general, we say these three groups would spread out in that plane, right, in that flat sort of surface, to be 120 degrees away from each other. All right. So that's 3 electron groups. Now, we also have 4 electron groups. And in Chem 1, we have 5 and 6 electron groups, but we won't worry about that here. Just to come back and actually give you the details that I was looking for, the double bond character in formaldehyde here actually compresses the angle, and this should really be drawn more like this. This angle here and this angle here, because of the double bond having more electrons in it, is actually going to be about 122, making this angle here about 116 instead of 120, 120, 120. But that's just because that's what double bonds do. I got another example of a linear molecule. This is acetylene, or ethine. C2H2. Acetylene is its common name. Ethine is its organic name. You can see here on this carbon, it has a triple bond and a single bond, 2 electron groups. So the bond angle is 180. This carbon has the same angle, triple bond, single bond, so also 180. So that just means the whole molecule is linear. It's all straight molecule. So you just pick an atom, and then you look at the geometry around that atom. We would look at the geometry around this oxygen and say that that has actually 3 groups around it, 3 trigonal planar. So if we could imagine, at the end of that carbon dioxide molecule, the lone pair electrons should be arranged in a planar configuration, all within the same plane and all 120 degrees away from each other. Okay, so going back to the 4 groups. So 4 groups around it we call tetrahedral. And the bond angle here is 1095. Now you might say, no, that bond angle is 90. Well, that's in a flat surface. If you take 4 groups and you put them out as far away from each other as possible in a flat surface, in a plane, then yeah, 90 degrees is the best you can do. But since we have 3 dimensions we can take advantage of by simply pushing one of these hydrogens, forward out of the plane, and by sticking one of these hydrogens backward into the plane, while keeping these 2 flat with our, our board, we actually can get them further apart. We can get them 109.5. So that's what happens. The name comes from the geometric shape that has these 4 triangular faces on it. Think of it as a 3-sided pyramid, but the bottom side also counts. The repulsion of the 4 groups is what separates it to the 1095, and we have 3 different flavors that this comes in. And actually, we have a few different flavors that this guy comes in too, and I forgot about that. So there's only one kind of linear, regardless of if you have one of your groups being a lone pair. Right? 1 bonding pair, 1 lone pair versus 2 bonding pair. You're both still called linear. But in trigonal planar, sometimes you have this situation. In SO2, we have a situation where we have 3 electron groups. And one of them is a lone pair. We don't call, so we have 2 different terms. We have the electronic geometry term, which is what these are: linear, trigonal planar, tetrahedral, and so on. But then we have a molecular shape name. And the molecular shape name in the case of linear is the same. The electronic geometry equals the molecular geometry because they're both just called linear for linear. But for these compounds, if you have all bonding pairs, we call you trigonal planar. But if you have 2 bonding pairs and 1 lone pair, we call you bent. And that's because if we were to simply see the arrangement of your atoms, you would look bent. It would look like this, right? These atoms are arranged in a bent way. There isn't a, third part over here that makes it look like a symmetrical, 3-pointed frisbee, which would be the trigonal planar geometry. So when that atom's not there, then we just see this bent little molecule. This is important because with our tetrahedrals, we have 3 different flavors as well. We have the tetrahedral with 4 bonding pairs, which just gets the name tetrahedral. We have the situation where we have a lone pair, where one of those is a lone pair, and we call that trigonal pyramidal. It's a triangle or 3 trigonal base pyramid style shape without an atom at the top. If there was another atom at the top, it would look like this and be called tetrahedral. The third kind is when we have 2 lone pairs. So again, 4 bonding pair, 0 lone pair, 3 bonding pair, 1 lone pair, 2 bonding pair, 2 lone pair. When we have 2 lone pairs, we end up with the same sort of thing. We get a molecule that looks bent. And so the name bent is repeated for trigonal planar and for tetrahedral. It just means different things when we're talking about different electronic geometries. All right, so how do you predict what kind of shape your molecule is going to have? Well, you look at the, like for water, you would look at, you only look at the electrons, then you get the electronic geometry, and you get that it's tetrahedral. If you look at the arrangement of the atoms, we see that it's bent. And again, the way that you can figure that out is either just looking at this table, or you could, kind of memorize it. But you would draw a good Lewis dot structure first. That's crucial, is that you have to have a good Lewis dot structure. If your Lewis dot structure is incorrect, or you don't have enough electrons, or if you don't have octets, well then of course your geometry and your electronic geometry are going to be off. All right. Should we try one? Let's try one. So let's draw, or let's determine the molecular geometry of ClO2. Now ClO2 minus is chlorite. Now chlorine has 7 valence electrons. Oxygen has 6 times 2 is 12, and we've got an extra one. This looks like it's going to be 20 electrons. So we've got chlorine in the middle, oxygen on the side. Let's go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Looks like everybody has an octet here. So then let's do the geometries. Electronic geometry, how many electron groups? Well, we've got a lone pair, 2 lone pair, bonding pair, 2 bonding pair. So 4 groups. tetrahedral. Now we look at the molecular geometry. Of those four groups, how many of them are lone pairs, how many are bonding pairs? Since there are 2 bonding pairs and 2 lone pairs, that is bent geometry. So this molecule would most likely look something like that in nature. Let's do one more. Let's draw the structure and geometry of NO2 minus. So this is nitrite. So 5 for nitrogen, 6 for oxygen. There's 2 of them, plus 1. So 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Not enough for nitrogen, so we're going to need some from somewhere. Let's take them from this side and make them into a double bond. Now we could, of course, have done the other side, so this would have 2 resonance structures. Now let's look at the electron groups. We've got a double bond, a single bond, and a lone pair. So electronic geometry, there are 3 groups, trigonal planar. Molecular geometry, of those 3 groups, we've got 2 bonding pairs and 1 lone pair. So this is bent. All right. So polarity, let's talk about polarity. Actually, it's a good moment to talk about how molecular shape influences how we taste. Molecules of food, right, interact with our taste buds. And so different molecules and their level of interaction actually determine the signal that gets sent to your brain. So sucrose, for example, which is a table sugar, we can metabolize that, we get energy from it. But there's some artificial sweeteners, such as saccharin, that don't get metabolized at all. They just pass through our body. And they don't have any caloric value. There is some that have some lower caloric value, like aspartame. But the way that these work is that they interact with the same taste bud that recognizes the molecule glucose. And because of the shape, it can actually bind better to that receptor site on your taste bud. And because they bind to that active site more strongly, we get a sweeter sensation. And it actually takes about 200 times as much sucrose as aspartame to trigger the same amount of signal that we send to the brain. So then, talking about electronegativity and polarity, let's talk about why oil and water don't mix. So if you combine oil and water, they separate into distinct regions, and the reason for that is because the water molecules actually bunch together and they push all the oil molecules away. And water does this because of the fact that it has uneven sharing between the bonds. Let's see, do I have a molecule? I do have a molecule. The 2 bonds between O and H, they're an electron pair that's being shared, but because oxygen is more what we call electronegative, it kind of pulls those electrons more to its side than the hydrogen gets, on its side. And so that ultimately results in the oxygen having more of the electrons around it and more of a partial, this little symbol here is for partial negative charge, while the hydrogen itself is left with a more partial positive charge. And we call this electronegativity. It's the ability of an element to attract electrons, or the force in which electrons want to go to a particular element. And oxygen is more electronegative than hydrogen, and that just means on average the shared electrons are more often by the oxygen. This results in what we call a dipole moment. It's an uneven sharing of electrons, so we get a charge separation within the bond. And these dipole moments can be on a scale. They can be really strong and they can be really weak, but the magnitude of those dipole moments will determine whether or not molecules are what we call polar. So let's talk a little bit about the differences here. So Polar covalent bonds, polar covalent, have dipole moments. And the magnitude of the dipole moment depends on the electronegativity difference between the two elements. And here is an electronegativity table, and the numbers underneath the elements are those electronegativity numbers. So you would just take the difference between the two. So oxygen is 3.5, hydrogen is 2.1. So this leaves a 1.4 difference in electronegativities. Now we're going to talk about the scale at which you could use to determine if that's polar or not. So for a fixed bond length, the greater the electronegativity, the greater the dipole moment. So the values are kind of assigned based on fluorine. Fluorine has the most electronegative sort of properties. It was given an electronegativity of 4 sort of arbitrarily, and everything just is compared to that. So the 4 doesn't mean anything, but it's just the biggest electronegativity, and then it goes down, you can see, as you move away from it. Two elements with identical electronegativities would form a covalent bond that shares electrons perfectly. So 2 chlorines or 2 carbons or 2 nitrogens wouldn't be hogging the electrons at all. There would be no lopsidedness in where the electrons are. We would call this non-polar because it doesn't have poles, right? There are no poles with charge on them. Compounds that have a large difference in electronegativity, so large in fact that they just transfer electrons to each other, are what we call ionic bonds. These are nonmetals and metals. They essentially are so different in their electronegativities that they just give each other or take away the electrons. And then there's the middle ground. These are the polar covalents. So these are the ones that are an intermediate electronegativity between perfect sharing and just giving away the electron. HF, for example, the electrons are shared, but the shared electrons are more likely to be found on the fluorine than in the hydrogen. This is a polar covalent bond. And so in order to tell, you look at your electronegativity difference, and then if that range is 0 to 0.4, then we would just say that that's a pure covalent bond. If it's 0.4 to 2, we would say it's covalent, polar covalent or polar bond. And if it's larger than 2, we would generally say that that is an ionic bond. And so that's kind of the way we decide if something is an ionic bond. Before we used to just say it's a metal and a nonmetal, but now it would be more quantitative. We'd look at the electronegativity numbers. So does the presence of a polar bond always mean that your molecule's polar? The answer is no. A polar molecule is one that has polar bonds that add together to cancel and don't cancel out to form a net, what we call dipole moment. So in this example, these are 2 polar bonds. The bond, you can go back and look at the electronegativity. Oxygen is 3.5, carbon is 2.5, so that's a delta En of 1. So that's well within the range of polar. So that's a polar bond. So we've got electrons, and we usually represent it with these little plus-sided arrows that point to the negative side. So there's a negative charge on that oxygen and a negative charge on this oxygen, and a kind of positive charge on the carbon. But because they're in opposite directions from each other, it's kind of like if I was standing, in the middle of 2 people pulling on me with ropes, right? Or 2 cars. This is a car moving one way, car moving the other way. They're going to rip me apart. 2 carts that are not very strong, and they're both trying to pull in opposite directions. Well, what direction am I ultimately going to go in? If they're pulling the same in both directions, I'm not going to go anywhere, right? Because this direction cancels out this direction. And so that's what's happening here. The electrons in this oxygen are trying to pull, the oxygen's trying to pull the electrons toward it, but so is the other oxygen. And so the electrons just get to hang out right there instead. So this is not a polar molecule because of the fact that the directions cancel out. Now there are directions that don't cancel out. Here's an example. For other reasons too, this has 4 electron groups. 2 of them are lone pairs, and they exist in these little shells. So right off the bat, you can see this is lopsided already. There's more electrons on this side than there is on this side. But also, the 2 pulls, the 2 bonds that we're looking at, they both add up to the same direction. They both end up with a net this direction of electrons because they don't cancel each other out. So here are some of those shapes that do cancel out. So you can see here when it's linear, as long as the molecule is the same atom, no problem. So if this was, so here's a linear molecule, Cl and Cl. This is going to be nonpolar. On the other hand, H and F, this is also linear, but this is definitely a polar molecule. So the atoms are not the same. That's usually your first clue that it's going to be polar. Let's look at a nonpolar. This is trigonal planar. This is like N with a bunch of O's on it, right? That's totally fine. And this is a nonpolar molecule, even though the bonds themselves might be polar in those three directions. Now, substitute one of those O's for something else, and now it is not the same. This direction and this direction are not the same as this direction, and so that would make it polar. Any molecule that has 3 electron groups like that and a lone pair, let's just say it this way, if you've got lone pairs, you're automatically polar. So that includes the bent molecules, and that includes the trigonal pyramidal. But if you are tetrahedral, trigonal planar, or linear, then you may be nonpolar even with polar bonds. I'll show you an example. Carbon with 4 hydrogens, those are not polar bonds, so this is not a polar molecule anyways, so it's nonpolar. Carbon with 4 chlorines, these are polar bonds. Chlorine is more electronegative than carbon. But because they're all in opposite directions in the 109.5 degree structure, they cancel out. So it's still nonpolar. Substitute one of those chlorines for something else, and now this molecule is not symmetrical. The pool in this direction does not cancel out all of these directions. So you got to pay attention to the atoms. You got to pay attention to the geometries. Electronegativity and polarity are why oil and water don't mix. The water molecules are polar. The molecules that compose oil are generally nonpolar. Polar molecules interact strongly with other polar molecules, just like magnets interact strongly with other magnets. Non-polar things tend to gather together because they usually get pushed away by all of the other magnetic things or polar things that are clumping together. And so we just get some segregation here of the different types of molecules based on their polarities. Soap molecules are really cool because a soap molecule has a mixture of 2 types of molecule. It has a long portion here of non-polar bonds that acts as the non-polar side. This is what interacts with grease and all the grime on your dishes and that kind of stuff. And then it's got a polar head. This part is the part that likes the water and that attracts the water and lets the water actually bind to this molecule. This is how water can wash away grease, because the water binds to the polar part of this molecule, which is binding to the greasy molecules, and so it's an intermediate. It allows you to be able to form mixtures of oil and water, and mainly to wash them away. All right, so in review, we talked about Lewis theory, chemical bonds, we looked at molecular shapes, and we talked about electronegativity. So remember, electronegativity refers to the relative ability of the elements to attract electrons, and it increases as you move to the right and up on the periodic table. When 2 nonmetals of different electronegativities form a chemical bond, they are not evenly shared and it could be polar. In diatomic molecules, a polar bond results in a polar molecule. With more than 2 atoms, they may cancel out, so that's what you need to look at, and that's what we were kind of talking about. All right, hopefully these learning objectives give you an idea of what to study, and that does it for this video. I will see you guys next time.